it's fine. Here we are going to have another column here. Okay, because each and every substance must form a column. Okay, completing, like I always say, completing the KC table is as good as completing a puzzle. It is as good as completing a puzzle. You start with the obvious pieces of the puzzle. When you are playing the puzzle, you normally start with the corners. Here you start with the given quantities. Then from the given quantities, you go to the unknown quantities. Right, so consider, okay, let's start from here. X moles of A, gas A. It's unknown. So we'll take it as X. Even in the table, we'll put it as what? As X. Right, our ratio? 1, 2. Initial moles is X. Initial moles of B, 2. The product? 0. Right, so the initial number of moles of the product will be 0 because we are considering this reaction from the beginning when only A and B has been added into the container. There is no AB that is present yet, so the initial number of moles will be 0. Okay? At equilibrium, 0.4 mole of gas AB. Gas AB is here, so that is our 0.4. Right. I have exhausted everything that is given that can be included in the table. Our KC value cannot be included in the table. I will show you how we are going to use it. So we have our equilibrium number of moles here and the initial number of moles. We can calculate the change. Our change, as usual, is delta N equals N final minus N initial. Right, 0.4 minus 0 will give us positive 0.4. Right? From there, we can determine the changes of the other substances, making use of the ratio. 2:2, same ratio. The change here will be 0.4, but with a negative sign. 2:1. Whatever comes here has to be the half of 0.4, that is 0.2 negative. Right, from there we move on to equilibrium number of moles. X minus 0.2, we just write it as X minus 0.2. 2 minus 0.4.
1.6.
Equilibrium concentrations of the substances, X minus 0.2. The volume is 1. Okay, so if we divide by 1, it remains the same. It's not going to change. So we leave it like that. 1.6 divided by 1, it also remains 1.6. 0.4 divided by 1 also remains 0.4. These are the concentrations at equilibrium, but with our X being unknown. Okay, right. Let's move on to the KC expression. Let's move on to the KC expression. KC